Hi, thanks for tuning in. In this presentation, I'm going to talk about a project that we did at the University of Michigan in collaboration with a number of colleagues at a bunch of institutes listed down here regarding the potential of earthquake and tsunami early warning in Indonesia and the Indian Ocean Basin using a smart cable technology. I'll get to what smart cable technology is later on during the presentation. So first of all, what do we know about the natural hazards in Indonesia? Here, I'm showing a map of the Indian Ocean Basin. On that, I've superimposed a map of population per square kilometer. And you can already see Indonesia here, shown in the red rectangle, is very highly populated. Here on the left, I'm showing the map of the country of Indonesia in yellow. And as you can see, it covers a really wide range of area in the form of various islands. Now, the first thing that pops into everybody's mind when thinking of natural hazard in Indonesia is obviously earthquakes. This movie is made from the earthquakes larger than magnitude 6 from the USGS catalog dating back from 1900 until now. There's a whole bunch of uncertainties into this, and there are issues regarding the completeness of catalog, but this is fine since it's meant to show you that Indonesia is incredibly seismic. Just by looking at this, you realize that there's a whole bunch of seismic activity going on there. So here, in fact, if you just get all the earthquakes from the USGS data set, as I'm showing here on the left, you can do all sorts of seismic hazard analysis. Interestingly enough, not very much has been done here regarding the hazard analysis of Indonesia. Pretty much all of the studies date back or refer to this particular study by Peterson et al., the USGS in 2004, which basically they just went ahead and chopped up Indonesia into a bunch of zones, 3.5 zones, if you wish. Interesting, but lo and behold, this study was done right before the occurrence of the 2004 catastrophe, the magnitude 9.3 earthquake. Here I'm showing the rupture area of that earthquake in red. The yellow star is meant to show the epicenter of that earthquake. When you examine this critically, you realize that while they've got the epicenter right, the entire area of the rupture almost is off in the zoning regions by Peterson et al., which is problematic. Now, if you take the earthquakes, for example, in any of these zones, I'm taking zone 1, and do a sort of Gutenberg-Richter, quick and dirty Gutenberg-Richter magnitude frequency distribution, you realize that, as I'm showing here in the bottom, if you use a magnitude 4 as a magnitude of completeness, as the USGS would like you to believe, you'll end up with a b-value of about 0.9. But then if you change it to about 4.5, you end up with a magnitude with a b-value of about 1. Now, this doesn't mean that there's a problem inherently with a b-value of less than 1. A global b-value of 1 is an artifact of a bunch of assumptions that people make in terms of this kind of equation. But it just tells me that there is a problem in the lower magnitude range. Either I'm recording a not enough number of small earthquakes, or there is some sort of a problem in the declustering techniques that I use. My money is on the former, because obviously, if you look at this plot that goes to the magnitudes of like 2 and 3, you see the huge problem of deficiency in the number of earthquakes. So there is a problem there. We need enough instrumentation in the region to record smaller earthquakes. So this was for earthquakes. What about tsunamis? Well, if you take the tsunamis from the NOAA dataset, as I'm showing here with pink stars, you realize that there's a whole bunch of tsunami stuff going on here in the region. So tsunamis also need to be taken very seriously if you're doing any sort of natural hazard analysis in the region. Now, what about cyclones? Here I'm superimposing the cyclone tracks on this map, and again, you see that Indonesia is almost immune to cyclones, which is not really surprising because the equator is sort of passing through the middle of the country, and it means that the Coriolis effect is going to be very minimal. Ergo, you will not have as many cyclones in the region. So the major concern for this region are earthquakes and tsunamis and natural hazard analysis. So first of all, earthquakes. One of the customary things that is done nowadays routinely for this kind of business is tectonic blocks. And the idea it just goes back to to 1975 in a study by Ando, when he was looking at the seismicity of the Nankai Trough, and he was going through the historical archives as well as the available seismic data in the 70s. He realized that the entire subduction zone does not really need to break during an earthquake. It could be just one single block or a number of blocks or all of them together. There are all sorts of permutations possible here in this problem. And we nowadays use this, again, as I said, routinely. You can apply this idea, this sort of brilliant idea, to Indonesia. This is a sort of a patchwork map of the ruptures that have happened during various earthquakes in the region. And this is mainly from historical archives and the seismic data interpretation. And you realize that there are gaps here, there are incompletenesses here and there. It could be either a seismic gap, or we don't really have that much data to address the problem. In order to study all of this and sort of detect these earthquakes in the future, we have all sorts of seismic stations in excess of about 140 stations in the region. And you look at this closely, and you immediately see this skewed distribution of these stations. We don't really have any stations to the west of the trench that I'm showing you there with this black line. There is almost no stations in this region. To the best of my knowledge, there are no deep ocean bottom seismometers to use permanently in this area. Now, to add insult to injury, if you just add the epicenters from the USGS dataset to this map, you realize again all the earthquakes are happening. Not all of them, but most of these earthquakes are happening to the west of the seismic network, which means trouble. We need to cover this area and this to the left, to the sort of closest seismic gap. And well, the no-brainer, well, like the thought experiment would be just, why don't you just put all kinds of stations west of the trench and close the deal? This looks really like sci-fi, because who in their right mind could afford to do all sorts of these things, put all these stations to the west of the trench? But it is not really sci-fi. This idea, which has been explored recently, is called smart cables, as sort of the answer to this need. SMART stands for Scientific Monitoring and Reliable Telecom, which basically means you take a telecom cable. If you want to deploy a telecom cable, just put all kinds of scientific instruments on this telecom cable, and the cost of everything, like the cost of the the power supply, the data acquisition, everything is just going to be covered by the telecom companies per international and governmental agreements. And you can measure everything: pressure, temperature, seismic exploration, you name it. And these green nodes that I'm showing here in this map are basically the repeaters that are installed on these cables that are sort of boost the signal. You can just put the instruments there and measure everything at that point. Now, you look at the distribution of these cables, the subsea cables globally, and this is extremely good news, because this map is color-coded according to population. You realize that whenever there's highly populated and there's a subduction zone, i.e. there are earthquakes, you have a very high density of these cables. So you can use these cables to do all sorts of early warning or early sort of detection of marine hazards. Now, going back to Indonesia, this is just an example of the quote-unquote magic of the smart cables. This is a current coverage of seismic stations. I'm showing the seismic stations with white triangles in this maps, and the earthquakes are color-coded according to the primary azimuthal gap that they're experiencing. The sizes correspond to their magnitude. Now, you realize that there are a whole bunch of red here, which means that the azimuthal gap is really small. But as you move away from this central population region, you realize that you're moving away from ideal, i.e. the small azimuthal gap. Now, if you add to this, in order to cover this huge azimuthal gap, if you add to this the smart cables as you're proposing, you immediately realize that the azimuthal gap is very, very small. Now, admittedly, there are a bunch of outliers here that I'm showing here in this yellow ellipse, and these are either small and far from population centers, or these are strike slips that don't really pose a tsunami threat to the populations. I'll get to this later on in the presentation. Now, so just to put some numbers on this, these are the some histograms showing the number of events as a function of primary azimuthal gap before and after the deployment of smart cables. I'm just calling the current existing network IRIS, and you immediately see again that there is about 140 degrees decrease in the azimuthal gap. This is very important and good news if you're trying to detect these earthquakes, trying to model the rupture, trying to map the rupture area. This is excellent news. Now, so this was some statistics. Can we do this in a more systematic and deterministic way? Well, if we can just build a small data set of a number of ruptures. Here I'm building a number of rupture scenarios that could happen in the Indonesian Java region. The first model, called Model 1, is the 2004 Sumatra earthquake. This is the rupture area from the USGS data set. Then there is this Model 2, which happened in 1883 in Sunda. Model 3 is the 2007 Bengkulu earthquake. This little blob here. Model 4 is the long anticipated Padang earthquake that is supposed to happen in the seismic earthquake, hypothesized to happen in this seismic gap in Padang. Model 5 is the same thing, just extended due south. This is a much larger earthquake. And Model 6 here, in the absence of serious seismic constraint in the region, In Java, we just put the worst case tsunami scenario, rupture scenario as a sort of a magnitude 9 plus earthquake there. So these are the scenarios that we have. Now, in order to monitor all of these things, we can add stations. Here are, again, the same iris plus the smart stations here. And the detection-wise, how fast we can detect these things, we can do a simple analysis, sort of travel time analysis from these complex ruptures to these stations. Here I'm using a simple 1D velocity model, AK135. You can do more complex things, but here, again, in the absence of comprehensive velocity models, I think this model will do just fine, especially at short distances. Now, here I'm showing all of these 6 panels. Each of them belong to each of the 6 models that I showed you. These panels show the number of detecting stations, number of stations that detect the P wave as a function of time. I can do S waves, different types of waves, but P waves are primarily used in terms of earthquake early warning because they travel much faster, they arrive fast, and of course they're less sensitive than, say, S wave to the heterogeneities in the region, so they're more robust. Historically, traditionally, they've been used more robustly in this fashion. Now, again, the Iris and Smart cable, the combination of these 2 cables are shown by a red curve, whereas the existing network is the product of the existing network is shown in blue. And you look at this and you realize as a median of about 10 more stations are added to the network coverage for each event, which is excellent news, especially if you're considering the physical distribution to all of this. Now you can do all sorts of other statistical analyses, such as the famous delta U analysis to all of this, but this sort of makes the case that this sort of analysis is useful. Now, another piece of the puzzle, we can use this offshore network to do study of seismic acoustic signals. Seismic acoustic signals are these sort of PRS waves that are converted to P wave on coastal slopes, and the P wave just gets trapped in a sort of a low velocity zone of the surface, near the surface of the ocean. It's called the SOFA channel. It had a pretty high frequency content due to sort of being the nature of the guided wave, just bumping up and down in the channel. Now, this is not the smart cable, but it gives you an idea. There was a DAS experiment in Senriku, Japan, in November 2019. It recorded a bunch of earthquakes in Chile and the southeastern Pacific. And you can see, as you can see here on the right, the T waves are making a beautiful signature in these maps at the exact right arrival time and exact sort of frequency window. Now, so this was for earthquakes. How about tsunamis? Well, I think to be on the same page, it's best if I just provide you with sort of a quick and dirty crash course on how we do things in the tsunami business. When we're studying tsunamis, as a sort of a long sidebar, first of all, we need a source, right? The source could be anything. It could be underwater landslides, it could be earthquakes, it could be some sort of meteorological phenomenon. But here, for the purpose of this talk, I'm just focusing on earthquakes in this framework or model is a dislocation source at the bottom of the ocean from they produce a dislocation here. And here I'm showing the universe in 3 layers. The bottom of the ocean, or lithosphere, if you wish, is called. I'm showing it in brown, the ocean floor. On top of that, I have the ocean, the layer of the sea, the ocean, and below that is pretty much everything else in the world. Now, during an earthquake, earthquakes happen along the fault line. There's a relative sense of motion here, and here I'm showing the mechanism of the earthquake with this beach ball. Those who might not be able or familiar with these beach ball things, this just showed this is a really convenient tool in seismology that you use in order to sort of show the mechanism of the geometry of the earthquake. Here, this black lines, black area, black surface, and this beach ball show convergence, to show sort of being pushed together. And this is because the energy is sort of getting the material here just sort of getting crammed, and this results in a deformation at the bottom of the ocean. Now here I'm showing the vertical component because the horizontal component is not going to cut the water. You cannot shear the water. You cannot cut through a liquid. And as a result of that, the strike slip earthquakes that are moving stuff horizontally do not really pose a threat here, as I mentioned before. This is why we consider only the vertical component. Now, we assume this is a big sort of big leap of faith, but we assume that this deformation is transferred, quote unquote, incompressible to the surface of the ocean, and the system of humps and troughs at the surface of the ocean sort of mirrors what we have at the bottom of the ocean. Now, this is going to be considered as the initial condition, as it's known in my tsunami models, and this is going to be a hydrodynamic propagation problem. You basically just study how this unstable system of humps and troughs, because it's gravitationally unstable, it cannot sit there forever, it moves around in the form of the tsunami. The result of all of this is going to be the tsunami. Now, by just looking at this problem, or sort of a setup that I'm showing here on the right, you realize that the shallower and the bigger the earthquake, the larger the formation at the bottom of the ocean will be. Now, there's a specific class of earthquakes, they're known as slow earthquakes, which are unusually deficient at higher frequencies, that as a result are going to be less dominant, let's say, in the magnitude calculation properties. And the seismic moment, the magnitude assigned for these earthquakes is often smaller than what should be, and as a result, the tsunami threat is more serious from these things. Now, the source of the earthquake is not always like a beach ball, because beach balls are nice, they're localized, they're beautiful. We can assign all sorts of properties and geometry to them very simply. But the Mother Nature is seldom very, very simple. As this is an example. This is the sort of a dislocation model on a fault during the 2011 Japan earthquake, and you can realize it's far from like a simple shape. It's very complex. Not super complex as it happens in complex earthquakes, especially larger ones. But you see, it follows a larger pattern, a more complex pattern. But even so, you can use fancier algorithm to again calculate this the ocean floor deformation from all of these things, and then again use the tsunami simulation programs in order to quote unquote predict the amplitudes or the propagation of these tsunamis. Now, this map on the right is color coded according to tsunami maximum amplitudes, and I'm going to use some of these maps, this sort of system of color coding according to this scheme later on in the talk. One of the features dominant in this map is called directivity, which basically means that the dominant azimuth of propagation of the tsunami is always perpendicular to the dominant direction of the fault. So here I have a northeast-southwest fault, and as a result, I have a sort of southeast propagation direction is sort of the peak of the directivity low. So this was for the source. What about the propagation? As I mentioned, tsunamis are gravitationally unstable systems of humps and troughs on the surface of the ocean originally. And this, as a result, they're called gravity waves. Gravity waves are a complex system of things that move around in the oceans or in the liquids. And here, a complex system of equations called Navier-Stokes equations, again, are used to solve them. A sort of a useful approximation to use to solve these things, I call it shallow water approximation. It means that the dimensions of the source is much larger than the water depth, which is typically the case for earthquakes. One of the byproducts of this assumption is that the speed of the tsunami is going to be given by this equation. It's beautiful because g is the acceleration due to gravity and h is the ocean depth at a given point. It means that you give me the depth of the ocean anywhere you want, and I'll tell you how fast the tsunamis move. You can plug in typical values into this. This will give you the roughly in the open ocean. It will give you roughly the speed of a jet plane. Now, it's nice, but there's a caveat to this. As the tsunami is approaching the coastline, it's a long wave. Remember, it's approaching the coastline. It's slowing down. Remember, because of this equation, when h becomes smaller, c has also become smaller. But eventually it stops. But then, where does the energy go, right? It's not like you're driving a car and pushing on the brake. Where does the energy go? And it turns out, so it's a long way that the head of the wave is sort of approaching the coastline, slowing down, whereas the tail of the wave is still moving fast. And as a result of that, the energy of the tsunami is sort of getting cramped in the smaller area, and the waves become larger. And this is what makes tsunamis dangerous, and it's called a shoaling phenomenon. So here I'm blowing the top end of this map. Here on the top, and here the tsunami is arriving from an earthquake to the left. And as you can see, the red curve, which is following the largest tsunami peak, is sort of getting picked up, as you wish, as it's arriving to the coastline. It's becoming larger and larger and larger. A simple analogy to this is a traffic pileup. Just imagine an array of cars. You're driving on a highway. The driver on at the head of this trail of car just pushes on the brake. The driver in the back doesn't really know, so it slows down. Whereas the tail of the traffic is moving fast. Here on the top, I'm showing you a made-up metric called car density, and it's just a number of cars per unit length. So if I run this little movie, you realize that the density of cars sort of accumulating until a traffic pileup happens. You end up with something with a cramped number of cars per unit length, as happens for the tsunamis. Now, that's what source and propagation. How do we detect tsunamis? They're typically nowadays detected, if you wish, or let's sort of measured by DART stations. DART is a global network of ocean bottom pressure sensors. They just constantly measure the pressure of water, and when a wave passes over, let's say tsunami wave, they measure the overburden from that, or incremental overburden from that wave. And as a result of all of this, the tsunamis can be modeled. Now, this is a global coverage of DART stations, and as you can see, it's far from perfect. Statistically, a large number of these stations don't work, and they're very expensive to deal with. So there's a major room for improvement. So just to give you a really quick example DART and how it's expected to move, as was the case in 29th of July 2021 Alaska earthquake with a magnitude of 8.2. This was I call this DART at its best because the majority of DART stations in the neighborhood were working on that day, and just fortuitously. And here I'm showing on the map on the right, I'm showing the tsunami simulation from a complex rupture, the USGS solution for the rupture. I'm showing the tsunami simulation, and then all around it are the real DART data from that particular event. And if I run this little movie, you see there's a whole bunch of stuff going on here. There's a lot of physics in here. You can actually argue about different details of the rupture, but just looking at this data, including the directivity, including the propagation, including slip distribution of the rupture, a whole bunch of things you can actually use from this map to do. Now, the problems here are that, well, DART doesn't really work very well near the coastline. And it's an engineering thing. People have been trying to improve things. The new generation of DART is actually much improved in this regard, but there are still some problems when approaching the coastlines. Seismic contamination in the near field is a serious issue. This is also going to be something to deal with in the smart cable. In the DART, it's much more serious because you're directly dealing with pressure. And the Rayleigh waves, which are seismic waves, they're more effective on the vertical axis. They're going to interfere with the pressure signal. DART is also very costly, several millions of dollars for each stations to deploy and maintain. And just the logistic of maintenance is also going to be a serious issue here. So that was a really long sidebar. I hope you now have a good sense of how the principles of tsunamis work. Now, going back to Indonesia, what's the current situation? Here, I'm showing the existing DART stations in the region. Only one of these things is expected to be working now. These were all deployed in the aftermath of the 2004 catastrophe here in the region. Assuming that all of them were working during that tsunami, what could be expected? Now, this is a simple ray tracing experiment for the tsunami here. I'm just tracing the tsunami propagation set in azimuths. And the black tick marks here and these energy rays, if you wish, show 15 minutes of calculation. And you realize just the earliest this tsunami is detected by these DART stations is about an hour after the origin time, which is terrible. If you're doing tsunami early warning, if you want a realistic or semi-realistic measurement of a picture of the source, this is not going to be useful at all. So there's certain room for upgrade here. Now, if you go ahead and install the smart cable array that we talked about before, this is going to be comparatively cheap. It's going to cost us $350 million, but compare this to the economic loss, more than billions of dollars economic loss during the 2004 earthquake alone. And this is once deployed, they're going to work for about 20 or 2 or 3 decades, which is brilliant. And it's not just about tsunami or earthquake early warning. You can do a whole bunch of other measurements, as I mentioned before. So I can do a sort of similar analysis to what I did before, but for earthquakes here, I'm just using my old 6 ruptures. And in order to do a tsunami analysis, I am calculating the initial deformation of my tsunami's propagation. Remember, now this is going to be calculated from the source, and here I'm color coordinating the map according to deformation of the ocean floor in centimeters. Now I can use my tsunami simulation routines to calculate the propagation of tsunamis. These maps again are maximum tsunami wave heights here from these various models. The pink bars show the maximum coastal tsunami amplitudes in meters. Now, again, a similar analysis to what I did before. Here are the number of detecting stations as a function of time for each of these models. I'm just blowing up this little one bit to the left of this plot here. I'm showing it just for high resolution. And just looking at this, you realize that on average there are 20 detecting stations for each of these models on average. There are exceptions here and there due to relatively smaller earthquake size, but you just look at this and you realize that there's a major improvement. If you have 20 stations, 20 sampling points, like every 50 kilometers or so for the rupture, you can have a really excellent idea about how the rupture works and do all sorts of early warning. And just look at this. This is all done within the first 10 minutes of the earthquake, after the earthquake. Now, last piece of the puzzle, landslides. Landslides, as I mentioned, they can also create tsunamis. Landslides can get triggered by many things, perhaps most importantly by seismic activity. They're called seismically induced landslides. They're difficult to deal with because the triggering process is very complex and highly nonlinear. They're sensitive to pore pressure, which makes their analysis kind of tricky. They're sensitive to earthquake content, frequency content. Remember, I mentioned slow earthquakes are more prone to create larger tsunamis. Now, faster earthquakes, compared to them, they produce more shaking, and as a result, they're more prone to produce larger number of big landslides. And finally, the past history of shaking and also strain in the region is not well known. Usually, we've been recording seismic data for the past 100 years or so. We're not really making any significant measurements at the bottom of the ocean at this point in terms of the geomechanics, and so it's a tough call. Now, to give you a hint of how these things work, this is a distribution of the CMT solutions for the earthquakes here in this region. I can go ahead and calculate cumulative peak ground acceleration at the bottom of the ocean. I'm color coding this now according to PGA, and you see that this region has undergone a huge amount of shaking already in the past 100 years alone, and in excess of about 25% G cumulatively. And based on this and about the bathymetric slope at the bottom of the ocean, I can just design some landslide scenarios hypothetically, just to get an feeling of order of magnitude of what's going to happen during a landslide tsunami. Here I'm designing these tsunamis. I'm showing these design scenarios with black dipoles, and from these I can calculate the maximum tsunami wave heights. This is again a cumulative map of all of these, and you can see that the situation is not going to be great. I mean, in terms of hazard, unfortunately, there is going to be significant hazard, especially here in the center region. Now, so far, I hope I've convinced you that the Sumatra and Java subduction zone constitute the main sources of seismic hazard in Indonesia. And of course, there's a history of shaking the region, which poses a threat for landslide scenarios. And I hope, again, I've shown you that the addition of a smart station will significantly improve the existing seismic network coverage. And it's going to be very helpful in terms of monitoring, both very fast monitoring of tsunamis and earthquakes to produce definitive answers in order to, or let's say, more confident answers in terms of the dimensions and the hazard of the source. And finally, these things are simple cost benefit analysis show that smart cables are also cost effective. Here, I think I'll end it here with this little movie here. I'm showing a tsunami propagation from the 2004 complex kinematic source, and I'm showing the arrivals of PNS waves and the tsunami with different colors in this map. Again, you can see the smart cables are doing pretty good in terms of monitoring both the tsunami and the earthquake. Thank you very much for listening.